All right, the closed interval method. This is a way to find the absolute max and minimum values of a continuous function on a closed interval. Notice this has kind of been a theme here. We want to make sure we're continuous and closed interval. This method does not work if those conditions are not met. So the process we're doing, we want to find the values of f that are critical numbers, similar to how we just did in a previous video. Find the values of the function at the endpoints, because remember, endpoints could be your max, absolute max and min too. For example, if this was our graph, our absolute max ends up being the endpoint, and our absolute min is also one. So you got to check endpoints as well. Then the largest of these values ends up being your absolute max, and the smallest of these values is your absolute minimum. Okay, so first one we're going to do, find the absolute max and min of this. We need the derivative to find those critical values. So first thing, find the derivative, just using our little power rule here. The last one's a constant, so that's 0. Now to find our critical numbers, find out where this derivative equals 0. That would just be setting this equal to 0 and seeing what we get. We can do some factoring there. Looks like there's a greatest common factor of 3x we can take out. Remaining then would be x minus 2. Set them both equal to 0 now and see what you get. If we divide by 3, we're going to get 0. If we add 2, we're going to get 2. So those are two critical values. We also want to check where the derivative does not exist. In this case, it exists everywhere, so there's this function does not have any values where the derivative does not exist. There's no denominator, so we're not looking at anything there. All right, so now the next process, what we want to look at is we want to figure out, we want to test the two values we just found. We want to find what's f of 0 and what's f of 2. Those are our critical numbers. But those aren't it. We also need to check, in this case, f at -1/2 and f at 4, because those are our endpoints. Okay, and whatever the largest and smallest values are out of those are the ones we want to go with. One thing we probably should have done to start is just make sure this was closed and continuous. Definitely here it's closed. You can see all polynomials are continuous, so this should apply to that. We should always check that first. All right, so now to finish here, this is just going through and testing that. If you plug 0 in for all these x's, you're going to end up getting 1 as the value. If you plug in 2, -1/2 and 4, see what those get. One way to quickly check values on your calculator here is to use the graphing function. So what you can do is plug in the function for your y equals. Do that quick here. So once you have it inputted, you can get values from your table. You can go to your table settings, and then instead of having this auto do it, I'm going to change it to ask, because then we can put in the value we want. So now I'm going to go to my table, and you can see you can input whatever x value you want there to figure it out. So if we put in 2, it should tell us what f of 2 is. So f of 2 ends up being -3. And then again, that's just putting those values in there. If we were to put, +2 in there, that's what you should get. Let's find the other ones quickly here. The next one was at -1/2. I'll put it in as -0.5. That's 0.125, and then also what is it at 4? So we get this one would be 17, and this one 0.125. All right, so now we're checking what is the largest value out of all these. The biggest one is 17. So we would say our absolute max is 17 at f of 4. Or, sorry, not at f of 4, but at x equals 4. And then our absolute minimum is going to be the smallest value. Now this is a small number, but negatives are even smaller here. And so our absolute min is -3 at x equals 2. So in this case, our lowest value did occur at a local minimum here, because this ends up being a local minimum, being a critical number. Our maximum, though, it did not end up being at a local max, it ended up being at the endpoint. Let's try another one. We want to solve this analytically to find the extreme values. So first off, is this function continuous? Yeah, we can put any value we want in for x. Is it closed? Yeah, by the brackets you can see this is a closed interval. So our conditions are met. Next thing, we want to find those critical values. So find the derivative. Here it's using the power rule, so bring down the 2/3. New power is 1 less, that'd be -1/3. Now we're going to try to see, let's simplify that. I'm going to move the x down to the bottom, so this is the same as 2 over 3x to the +1/3. So our critical values, where does derivative equal 0? That's putting the top equal to 0. Well, here, if we put the top equal 0, where does 2 equal 0? 2 can't equal 0, so there is no values where the derivative equals 0, meaning there's no absolute local max or local min. But we also want to check, where does the derivative not exist? I think we are going to have a value here. If we put that denominator equal to 0, we can solve that. Divide by 3, cube both sides here to get rid of that power, and we get 0. 0 is a critical number, meaning that at 0, the derivative does not exist. So to check for our absolute max and min now, we want to check our endpoints. So let's f at our endpoints here. And then also at the critical number. What is it at 0? And then the biggest ones are critical number, the other ones are not. If we put 0 in there, 0 to the 2/3 is 0. If we put -1 and 3 in there, let's see what we get. I'm not going to go through, that's just 2 to check. I'm just going to simply put those in here. So if we got -1, notice I put in the parentheses here, to the 2/3 power. And we're putting this back into the original function when you want to find values. You get 1. And then if we do the same thing with 3, 3 to the 2/3, we get about 2.08 something. So which ones are maximum and minimum? Looks like our absolute max is right here. That was the biggest value. Our absolute min is at 0. This is an example of a graph here that has a corner or cusps. If you want to see it graphed out, you can see that's why we ended up not having a derivative at 0, because there's one of these corner cusps there. That does end up being the minimum, and then 3 would be our maximum. A couple more. Let's look at this one. Is it a closed function? Yeah, again, but by the brackets we can see that. Is it continuous? Well, natural log, you got to be careful with. There is some numbers that you can't take natural log of. Remember, you can't do natural log of 0. That's something that does not exist. If you try natural log of any negative number, those also do not exist here. So if we plug in those numbers 2 we're definitely fine. Even negative 2 though, we should be able to do that because that's natural log of 1, we can do that. So it is continuous as well. So now we should be able to apply this by finding derivative. Derivative, we've looked at derivative of logs. It's 1 over whatever you're taking the log of, but make sure you do chain rule. What's the derivative of the inside? 1. We don't need to write that times 1. So that's our derivative. Where does our derivative equal 0? Like the last problem, you can't have this, so there is no points here that work. Where's our derivative? Not exist. That's putting the bottom equal to 0. And so at negative 3. So now you want to check what these points are going to be. So we want to check our endpoints here. What's the function at negative 2? What's the function at 2? And then critical points. Now here, though, you got to be careful. Our critical point of negative 3 is not in our interval. So if it doesn't fall in our interval, then don't check it. So don't check any critical values if it's not in that closed interval. So it is a critical point, but because it's not in the closed interval, we don't have it. So here, just whatever the two endpoints is going to be the highest and lowest value. If you put in negative 2, it's going to be natural log of negative 2 plus 3, which is natural log of 1, which if you put in the calculator is 0. The other one, you get natural log of 2 plus 3, or natural log 5. Natural log 5, you can put in your calculator if you want, but it's definitely going to be bigger than 0. So our absolute min is this endpoint. Our absolute max is the other endpoint. So big takeaway from that one, don't check critical points that aren't in the interval. Last one, exponential here. Looks like we got a function inside another function, so we got to use chain rule here when doing this derivative. This one, we get derivative of the outside, same derivative with exponentials. Times, though, what's the derivative of that exponent? 2. And so now we want to figure out where's derivative equals 0. If we set this equal to 0, this derivative equals 0, we can divide by 2. How do we solve an exponential equal to 0? Well, you got to think what's the way we can bring that down? We can do it by natural logging both sides here. Remember, solving with exponentials, natural logs opposite here. That also lets us bring down our power here. So we got 2x now. Natural log of e is just 1. But then on this other side, we got natural log of 0. You can go ahead and try it on your calculator. You can't do natural log of 0 or negatives. And so there's no values here. This one doesn't have any values because natural log 0 does not exist. Where's the derivative? Not exist on this one. I don't think this one ends up having any values either, because this we can put whatever we want in for x here and we can solve it. There's no values that don't work. And so this one, like our last one, all you have to do then would be to check the endpoints, because this graph exists everywhere. If you remember, the reason we're not getting anything, if you graph an exponential, they all have this kind of shape to them. So does this one ever have a local max or min? No, it's just continuously growing, so it doesn't have a max or min. And then it exists, there's no corners, vertical parts, even though this is, as we keep growing here, is going to look to go vertical but never actually get vertical. And we don't have any, it's continuous, so we don't have any of those critical points there. So then you're, again, just plugging in the values to find this. If you put in 1, you're going to get e squared, whatever that comes out to be. If you put in negative 1, you're going to get e to the negative 2, which is going to be a small number. And so this would be our absolute min, and this would be our absolute max. Whatever it is here at 1 is going to be lower than it is at -1.